Hello everybody, today I will introduce our recent work which is about automatically reverse engineering the diagnostic protocols of modern vehicles. I am Le Yu and I come from Hong Kong Polytechnic University. The ECUs contained in one vehicle can communicate with each other by following the in-vehicle protocols. So understanding the in-vehicle protocols is very important to the security assessment and protection of modern vehicles. We select the vehicle diagnostic protocols as the target of this paper, since they are very commonly used by the repairman to read sensor values or control ECUs through the OBD port of the vehicle. For example, we know that Keyword Protocol 2000, KWP 2000, and Unified Diagnostic Service (UDS) are the two most popular diagnostic protocols. However, when we check the standards of these two protocols, we find that the standards only defines the low-level message formats. The vehicle manufacturers define the syntactic information, the semantic meaning of messages, and the formulas for encoding the return values. KWP 2000 and the UDS protocol are proprietary protocols. However, some of the attackers has used the diagnostic protocols to launch some attacks on the vehicles. For example, in 2013, the researcher Miller sent diagnostic messages through the OBD port to the ECUs of the vehicle. They can use these messages to pair the engine of the Ford or Toyota vehicles. Some of the researchers has proposed a method to reverse engineering the in-vehicle protocols. Mostly, some researchers propose to analyze the traffic generated by the ECUs to reverse engineering the formats of the CAN messages. However, they can only handle the CAN messages transmitted between ECUs. They cannot handle the non-messages that are transmitted by using the transmission loyal protocols. Moreover, they cannot recover the proprietary formats and formulas contained in the diagnostic messages. Some other researchers propose to analyze the mobile apps connected to the vehicles to recover the possible request messages. They do not analyze the proprietary formats of these request messages. Moreover, the mobile app can use some formulas to extract the real sensor values. However, the app analysis-based method cannot recover the formulas used in analyzing the response messages. This picture shows the overall structure of a modern vehicle. The vehicle contains many ECUs, and these ECUs are connected by using the bus system, and all of them are connected to the gateway. And one vehicle will also has one OBD port connected to the central gateway, so that the repairman can use some professional diagnostic tools to communicate with the ECUs. The assumption of this paper is we only have the target vehicle and a diagnostic tool that can work for this vehicle. Reverse engineering the diagnostic protocols are very useful in launching some attacks. We used the professional diagnostic tools to send some messages to control the ECUs of 4 vehicles. For example, for the Toyota, we can successfully use the CAN messages to unlock all the doors. We can also modify some sensor values. This picture shows the OSI model of the most popular diagnostic protocols, KWP 2000, UDS, and OBD2. We can find that these 3 protocols are based on some transporter or network loyal protocols. This picture shows the overview of our system design. We can find that our system can be divided into 2 parts. The first part is called data connection, and we will use one professional diagnostic tool to read some sensor values or control some ECUs of the vehicle. During this procedure, we will use one computer to record all the CAN messages transmitted between the diagnostic tool and the vehicle. We will also use one camera to record the GUI of the diagnostic tool so that we can analyze the text or sensor values displayed on the GUI. After the data connection, we will analyze the diagnostic frames to recover the raw payload of the request and response messages. And we will also extract the field values contained in the request messages. We will also analyze the text showing on the GUI of the diagnostic tool. We will use some OCR to extract all the UI texts. Finally, we combine the field values extracted from the request and response messages and the text extracted from the GUI of the professional diagnostic tools to recover the semantic meaning of the customized fields in the request messages. We will also use some genetic programming methods to recover the formulas used when processing the response messages. This picture shows the steps contained in the data connection. Since one vehicle can contain many ECUs, and each VCU can contain a large number of the sensor values that should be connected during the data connection. To speed up the data connection step, we use one robotic arm to click the GUI of the diagnostic tool automatically. In detail, we will use one camera to monitor the GUI of the diagnostic tool. And after taking pictures of the GUI, we will use some OCRs to analyze the text showing on the GUI. And we will identify the target ECUs or ECU sensor values on the GUI. Finally, we will guide the robotic arm to interact with the GUI of the diagnostic tool. When recording the CAN messages generated by the diagnostic tool and the vehicle, we will add timestamps to each connected CAN message. We will also add timestamps to the video of the GUI. After connecting the diagnostic frames, we will need to recover the payload of the request and response messages and extract the field values contained in them. We will first filter out the frames that do not contain any parts of the request or response message. In this picture, we will filter out the flow control message since it do not contain any payload of the request message. After that, we will assemble the raw payload. For example, we will combine the data payload of the first frame with the data payload of the continuous frames together to obtain the raw payload of the request or response message. Finally, after obtaining the raw payload, we will extract the local ID, the DID, the ECU sensor value, or ECU control record. After obtaining the video of the GUI of the professional diagnostic tools, we will perform the screenshot analysis. We will first use the M-player to transform the video into a series of the messages, and then we can use the OCR to extract the text contained in each message. Sometimes the OCR software will miss some points. To avoid using the incorrect sensor values in the evaluation, we will use some predefined ranges to filter out the incorrect ECU sensor value. When reading the ECU sensor value, the requested message includes the DID or local identifiers that are customized by the manufacturers. We associate these DID or local IDs with the text displayed on the GUI of the professional diagnostic tools so that we can use the UI text as the semantic meaning of this DID or local identifiers. Similarly, when we use the diagnostic protocols to control the vehicle components, we can also use the UI text to explain the semantic meaning of the DIDs contained in the request messages. After receiving the response message from the vehicle, the professional diagnostic tools will recover the real sensor values by using some formulas. To discover which formula will be used, we design an improved genetic programming algorithm to infer the formulas. In the first step, we will construct the mapping between the ECU sensor values contained in the diagnostic messages and the ECU sensor values displayed on the GUI. This is done by using the timestamps contained in the recorded CAN messages and the timestamps contained in the video of the GUI. And then we can use the ECU sensor value contained in the diagnostic messages as the variable x. And we can use the ECU sensor values displayed on the GUI of diagnostic tools as the variable y. And we can apply genetic programming algorithm to infer the relation between the variable x and the variable y. Especially, we find that if the values of x or variable y are very small, for example, most of them are very close to 0, then the genetic programming algorithm cannot correctly infer the formulas. To overcome this issue, we customize the genetic programming by increasing or decreasing the values of the variable x or variable y. In the pre-processing, to evaluate the performance of our system, we selected 18 vehicles and 4 real professional diagnostic tools. Firstly, we measured the precision of OCR software for the 2 diagnostic tools. The precision of the OCR software reaches at least 85%. Moreover, we use the OBD2 protocol as the ground truth to measure the performance of reverse engineering formulas. And finally, we find that for all the 6 sensors, our system can obtain the formulas that are almost the same as the ground truth. For the 18 vehicles, we also used the 4 diagnostic tools to read 290 sensor values from the vehicle, and each sensor value contains 1 formula. And our system can recover 285 formulas contained in them. The precision reaches at least 98%. We compared our method with 2 existing formula inferring algorithms. One is called linear regression, and the other is called polynomial curve fitting. These 2 methods can only recover about 127 formulas and 93 formulas. For the 18 vehicles, we successfully used the professional diagnostic tools to control the ECU components of 10 of them. And for all of the controlled ECU components, we can recover the semantic meaning of the request messages successfully. Since some mobile apps connected to the vehicles can also read sensor values from the vehicle, we also perform static program analysis to recover the formulas from the mobile apps. Here we selected 160 mobile apps. Finally, we successfully executed the formulas from 28 mobile apps successfully. That's my presentation. If you have any questions, you can send an email to my mailbox.